Hello. In the previous sessions, we have seen how to represent the various processes in a TS diagram, and we could draw the TS diagram for gasoline as well as diesel engines. Now, in this video, we will try to uh, draw the TS diagram for a Carnot cycle, and from the diagram, or with the help of the TS diagram, we will try to obtain the expression for the efficiency of a Carnot's engine by two different approaches. Okay, so the PV diagram for a reversible Carnot's engine or Carnot cycle is represented at the bottom, which we have already used in the derivation of its efficiency. Now the Carnot cycle, it comprises of two reversible adiabatic processes and two reversible isothermal processes. So in the figure here, 1 to 2 represents reversible adiabatic compression. Then 2 to 3 represents an isothermal expansion. Then 3 to 4 represents adiabatic expansion. And finally from 4 to 1 represents again an isothermal compression. So these are the four stages, and the heat QH that is drawn from the high temperature reservoir is entering the working substance or the system during the isothermal expansion stage from 2 to 3, and the heat QL, which is rejected to the low temperature reservoir during the process or the stage from 4 to 1. Right? And the corresponding, if you are drawing the corresponding TS diagram, you can see that corresponding to 1 to 2, which is adiabatic compression, it's a reversible, so reversible adiabatic compression. Now reversible adiabatic process being isentropic, so 1 to 2 is representing the reversible adiabatic compression, which is isentropic in nature, so it's a vertical line parallel to the temperature axis. Now 2 to 3, which represents the isothermal expansion, it becomes a horizontal line which is parallel to the entropy axis, as we have seen. Then once again 3 to 4 will be the again an isentropic curve corresponding to the adiabatic expansion process. Then from 4 to 1, it is once again an isothermal compression, and it results in the corresponding horizontal line. So you can see it's quite remarkable that the TS diagram corresponding to a Carnot cycle will be rectangular in shape. The TS diagram for a Carnot cycle, it consists of two reversible adiabats and two reversible isotherms. Okay, and in TS diagram, the adiabats as well as isotherms. Adiabats are isentropic, and isotherms, both of them will be straight lines. So the TS diagram for a Carnot cycle is a rectangle. So that is a very, very important point to be remembered. Okay, there is no difficulty in remembering this fact. So it will be a rectangle. Right? Now, having understood the shape of the TS diagram for the Carnot's engine, we will be able to derive the expression for the efficiency of Carnot's engine by directly from this TS diagram. Okay, and let's do it in the next slide. So let me go to the next slide. So this is the same diagram that I have reproduced here. So this is the same TS diagram. So you can see that the entropy change during the two adiabatic process is 0. That is quite evident here, isentropy. So whatever entropy change is happening during the cycle, that occurs during the two remaining isothermal processes. One is the isothermal expansion, and the other one will be the isothermal compression. So as you can see in the diagram, the Q1 amount of heat is entering. Q1 amount of heat is entering the system, the working substance, during the stage from 2 to 3. 2 to 3 represents what is known as the adiabatic, isothermal expansion stage. Okay, so 2 to 3, this is thing. So I can say this is a Q1 amount of heat that is entering the system. Now during this heat transfer, since heat is entering the working substance, what should happen to the entropy? You can understand what should happen to the entropy. The entropy should be increased, because that is our idea. Due to the heat entering a system, the entropy of the system should be getting increased, and when the heat leaves the system, the entropy of the system will be getting what? Reduced. Okay, so let's see that in this case the entropy gain. So I can say the entropy gain okay, during isothermal expansion. How much will be that? Entropy change during isothermal expansion. So that is happening at a constant temperature, right? Okay, so at T1 it is happening, and it is reversible also. So what will be that one? That should be equal to, I can say, what is the heat entering? That is Q1. So we are writing using modulus values, Q1 by T1, is it not? Okay, it is a finite entropy change. That's why I'm writing Q1 instead of dq. dq corresponds to an infinitesimal heat, and the corresponding entropy change will be ds. Here it is some delta s. Okay, entropy gain that is happening during the isothermal, that is be Q1 divided by T1. Right now, in the same manner, the loss in entropy, you can see that entropy loss during isothermal compression. Entropy loss during isothermal compression, that will be how much? So it's given by the amount of heat that is rejected, that is Q2. So that is equal to modulus of Q2 upon at what temperature the heat rejection occurs. That happens at a temperature T2. Okay, so remember one thing, that we are using different notations. Okay, so just T1 is nothing but our high temperature, is not? In the temperature axis, T1 has been represented above. Okay, so T1 is nothing but TH, remember that. Okay, we could have used TH, but our note has already used T1, that's why T2 is TL. That can be clearly understood because the TL has been represented towards the origin. Okay, that is bottom. Okay, lesser value TL. Instead of TL, we are using T2. Instead of TH, we are using T1. Okay, that's all. No other differences. Right now, so you got it's Q2 divided by T2. Now, see, since the cycle is reversible, Carnot cycle is reversible. For being reversible, we have already proved this fact. Being reversible, what is the relation between Q1 by T1 and Q2 by T2? For a reversible cycle, this Q1 by T1 is equal to Q2 by T2, right? Okay, and now let's use our sign convention. Heat Q1 is absorbed by system, and so it is considered to be positive. Okay, Q1 is positive and Q2 is what? Negative. Is not? Q2 is rejected by the system, so it is what? Negative. So if you use the sign convention and I get rid of this modulus and all, so you can see that this expression will become Q1 by T1. Okay, and you take Q2, which is negative, from left side to the right side, so it will also become positive. So Q2, we have done this one before in the discussion of Closures theorem. Okay, Q2 divided by T2, that is equal to 0. Okay, so Q2 by T2, that's equal to 0. And so Q1 by T1 was the entropy gain, and Q2 by T2 is the entropy loss. So you know that see the net change in entropy is not. So that was delta S1 and delta S2. These two are the entropy changes actually. So you can see that delta S1 adds up into delta S2 as far as a working substance is concerned. Okay, and that gives equal to 0. So what is the conclusion here? That so the conclusion here is that the entropy change in the Carnot cycle, okay, the total entropy change in a Carnot cycle is 0. That's a very, very important conclusion, and it's nothing that is new actually. Why should it be so? Because you know that the Carnot cycle is one fact is that Carnot cycle is a cyclic process. Okay, it's a cyclic process, and moreover it's a reversible process, and we have seen that for a reversible, okay, it's not a cyclic process, the total entropy change, that is a closed integral of ds, that should be equal to 0. Okay, so entropy change in a Carnot cycle is what? 0, right? Okay, now let's obtain see, now means the entropy of the system will be remaining constant, that's all. Okay, so now let's obtain expression for the what do you say, the efficiency. So for that, let's we have to consider the heat entry and heat rejection. So for that, let's consider the isothermal 2 to 3, is not? So the isothermal 2 to 3. So this is what we are going to consider. So along isothermal or isotherm 2 to 3, along isotherm 2 to 3, what will be the entropy change? Whatever entropy change that is happening during the cycle, it is happening during the two isothermal process. During adiabatic process, it will not happen because entropy is a constant. So what is the change in entropy? So I can say S2 is not minus S1, or in general change in entropy, S2 minus S1, that will be equal to, what is S2 minus S1? That already we have written, that is equal to Q1 by T1, is not? Q1 by T1, that we have already calculated here, Q1 by T1 in terms of modulus. Okay, so from that, won't you be able to get what is Q1 is equal to? So what is Q1 equal to? So therefore Q1 will be equal to, Q1 is positive, Q1 is equal to simply S2 minus S1 into T1, S2 minus S1 into T1. Okay, so let me say that this is my equation number 1, right? Now similarly, along the second isotherm, which is isotherm that is from 4 to 1. Okay, if you consider the direction, it is from 4 to 1. Okay, doesn't matter. So similarly, along isotherm, you need to consider only the isotherms during which the heat transfer happens. That is quite easy for. Along the isotherm from 4 to 1, what is the entropy change? So I can write once again either S1 minus S2 or S2 minus S1. Okay, I'm just writing it as S2 minus S1. I'm bothered about the magnitudes here, S2 minus S1. Okay, so that is equal to, what should be that one equal to? That will be Q2 divided by T2. Is not Q2 by T2, the corresponding thing. So that is the entropy loss. I'm just writing its magnitude only. So therefore what will be Q2 is equal to? So Q2 will be equal to what will be getting? It will be equal to simply S2 minus S1 into what? Into T2. So that's my equation number 2. Remember that Q2, if you consider the sign, Q2 will be negative and Q1 will be what? Positive. Okay, that's the sign convention. But we are just taking its magnitudes here, so you need not bother much about it. Okay. Now, from, if you take only the magnitudes, okay, so from 1 and 2, can't you calculate what is Q1 minus Q2? That is Q1 minus Q2. So Q1 minus Q2. Okay, what will be Q1 minus Q2 is equal to? That is equation 1 minus 2. So that will be simply S2 minus S1 into T1 minus S2 minus S1 into T2 simply. Okay, or it's equal to S2 minus S1 is common here, S2 minus S1 into say T1 minus what? T2 into T1 minus T2. Okay, now Now, what is the this T1 minus T2 into S2 minus S1 actually? Okay, so T1 minus T2, T1 minus T2 means this much, right? And S2 minus S1 means this much. Okay, so is not this one, this area. Okay, and this will be the area. Okay, so and you have already concluded that the area enclosed by the cyclic process in the TS diagram will give you the net work done during the cycle. So we can say that this is nothing but equal to the work done, net work done, and that also conceptually true, because it's in any heat engine, you know that that is happening. That's very familiar for you by the time. So Q1 or QH amount of heat is entering the system, okay, and Q2 amount of heat is leaving the system, and the difference is getting converted into W. So here you have got Q1 minus Q2 here, so that is equal to W. The other way also. So either graphically or conceptually, this is nothing but what the work done during the cycle. So let me call that equation number 3. Now it's straightforward. What you have to do? You have to calculate the efficiency of the efficiency. Therefore, efficiency of the Carnot's engine. Therefore, efficiency of Carnot's engine. Okay, that represented by eta. What is eta equal to? Eta is equal to the work output divided by heat input. Here heat input is taken to be Q1, right? Heat entering, right? So that is equal to, what is that? What is W? Equation 3 says that is equal to S2 minus S1 into T1 minus T2, okay, divided by, what is Q1 equal to? Q1 you are getting from equation number 1. Okay, this is your Q1. This is Q1. That is nothing but S2 minus S1 into T1. So what happens? This S2 minus S1 will be getting mutually cancelled away, and what remains is T1 minus T2 by T1, right? So T1 minus T2 by T1, and that is nothing but 1 minus T2 upon T1. And remember, T2 is TL, okay, and T1 is TH for us. So this is same as what? 1 minus what? TL, right, by what? TH, using the notations that we have been using before, and which is nothing but the already established expression for the efficiency of a Carnot engine. Quite direct and quite simple. Okay, see that you recall our derivation of the efficiency of a Carnot engine using the expression for the work done during the corresponding processes that we have done in the I think the module number 3. So just compare, and you will find that this treatment is quite simple. Okay, this treatment is quite simple because the TS diagram, the basic reason why this treatment has become so direct and simple is because you can see the TS diagram for the Carnot cycle is a very easy geometrical figure, which is a rectangle. So it's quite easy to calculate the area that is enclosed by the a particular cyclic diagram. Okay, fine. Hope that it was quite simple. See, now in this discussion we have just considered what is the heat entry and other things. So we can even have a straightforward derivation for the the efficiency of a heat engine from the TS diagram, which is not much different from what we have done right now. But I think if you are running short of time, or in case you have to just use the TS diagram straightforward, you can use that one also. So let us check how to do that one straightforward. So once again, remember, it's the same derivation, but we are doing a bit more fast. Okay, so using the concepts. So here you have once again the TS diagram. So I have avoided all other labeling. only I have labeled it as some A, B, C, D. So the T1 is the TH here, and T2 is the lower temperature here. So S1 is the entropy initially, and S2 is the entropy finally. Okay, so you know it is just like this. It is cycle is going like this. Adiabats and also isotherms. It's rectangular in shape, and we expect that from the concept, this particular shaded area should give you the net work done, and there is a heat entry happening during this AB, and there is a heat rejection happening during what CD. That's what happened. Okay, so let's derive straightforward. Okay, so how to do that? Heat that is absorbed by the engine, right? Heat absorbed, you know, heat absorption that is happening. Okay, heat absorbed by the engine, what will be that one equal to? That will be given by, you know, heat transfer during any process is given by the area under that curve. Okay, so what will be that one? That will be the area under AB between the entropy axis, right? So that will be the area of what? I can say AB S2 S1 is not AB S2 S1 means the total area AB S2 S1. So up to here you have to take. Okay, this particular area will be, okay, this one I am not shading it now. This area is equal to the heat absorbed, right? That is area below AB. So, and you know, being a rectangle, that's also a rectangle, you can see. So what will be the area of that particular geometrical figure? That should be equal to S2. This width is S2 minus S1, and this height is simply equal to T1 from the origin, that is T1. So this is T1, this much height, so that will be equal to, I can say, T1 into S2 minus S1. Directly, geometrically you can get it, right? Now, heat converted into work. Heat converted into work, or work done, okay, in the TS diagram. How do you get it? That is nothing but the shaded area, right? Okay, the shaded area. So that is area of which rectangle? Area of the rectangle ABCD. These are all the concepts that we have already established. So what is the area of the rectangle ABCD? That is equal to the side. Okay, this side. This is the side. This side is nothing but T1 minus T2. So it's equal to T1 minus T2 into the other side is already established. That side is equal to S2 minus what? S1. So into S2 minus what? S1. Right? So you got whatever we need. Therefore efficiency eta is equal to, you know, the work output divided by heat input. Okay, heat input, work output by heat input. So we can use 1 and 2 for those two. So work output is given by 2, that is T1 minus T2 into S2 minus S1 divided by what is heat input. Heat input is given by 1, that is T1 into once again S2 minus S1 with same steps. You can see that by the time we have reached the same thing. Okay, and that's equal to T1 minus T2 by T1, which is nothing but what? 1 minus T2 by T1. Okay, or it's same as what? 1 minus T lower divided by what? T higher, the common expression or which we have derived earlier. So this is a much straightforward, okay, derivation without any complications and all. See, it's all optional, like that which way you have to do. So see, in exams, be careful. See, if you are asked to, depending on, this is my suggestion, if you are asked to derive an expression for the efficiency of a heat engine, see, it's always advisable, just refer to the weightage of the marks and the section from which, okay, the question is asked. Is it a section D, which corresponds to an essay type question? Then of course you can go for the first method. First means from the PV diagram. You see the lengthy method that we have done. That's always advisable because that is a weightage of mark that is given. Okay. Now, if the same question, derive an expression for the efficiency of a Carnot engine, if it is asked alone, Okay, maybe in a lesser mark weightage question in examinations and all, it's advisable for a 3-mark question or a 2-mark question. It's advisable to go for what calculating the efficiency from TS diagrams that too after discussing the related concepts, telling that the area under a process curve in a TS diagram gives the heat absorbed or heat rejected during the process, and the area enclosed by a cyclic process in a TS diagram gives the net work done. By after introducing those concepts in relation to a TS diagram, you will be able to derive the efficiency directly if it is not specified. So be careful and cautious while answering questions in your examination. Anyway, our aim of deriving the efficiency in this way, either the first method or the second method, is only to understand that TS diagrams are a very useful tool in obtaining thermodynamic informations in a quite direct manner. So hope that this discussion has helped you to understand the concepts better. Thank you.